So let's put things together now. Let's put our different sets of numbers together and investigate them a little bit further. We're going to return to some of the terminology we learned back in chapter 2 also. We've learned about whole numbers, integers, rational numbers, irrational numbers, and real numbers. And I'm going to put a little diagram up here. And it's kind of like a Venn diagram. It is a Venn diagram. And we're going to investigate this. And the first thing I'm going to note for you to help make sense of this is that we are going to use some capital letters to represent different sets of numbers. So the very first one we talked about was the whole numbers, the set of whole numbers. We're going to describe that with the letter W. Then we talked about integers. After that, we talked about rational numbers. And then we introduced the irrational numbers. We're not using a capital letter for those. And now we're going to put them all together into a group or a set called the real numbers. Now, just as a little refresher, whole numbers, those are like numbers that start with 0 and count up by ones. 0, 1, 2, 3, 4, 5. Integers are those, but also their opposite, so the negative versions of those. Rational numbers are numbers that can be written as fractions. Well, that includes whole numbers as well. And irrational numbers, we just talked about. They're numbers that are not rational, can't be written as fractions. And now we have this new one, real numbers. Those include every possible number that could be found with a line segment or represented with a line, number on a line. It's rationals, it's irrationals combined. It's everything. W is whole numbers, Z is integers, Q is rational numbers, and R is real numbers. Now, down at the bottom, you're going to see some notation that may look familiar. This symbol right there means proper subset. Proper subset means that the letter before is a smaller set than the one that comes after. It means there's elements in Z that are not in W. So W, the whole numbers, are a proper subset of the integers. There are integers that exist that are not whole numbers, right? We could say a whole number is 7, but an integer that's not a whole number is -2. -2 belongs out here, but not in there. And Z, the integers, are a proper subset of the rational numbers. -2 is an integer. It is also a rational number because it could be written as a fraction, but 3/4 is a rational number that could not be written as an integer or a whole number. So you see how these sets are embedded inside each other. And we started off way in the middle. We talked about the properties, but the nice thing is that every time we create a new property, it really, that's what created the need for a new type of whole numbers. There were properties that some sets have that others do not. It's why these other sets were developed. Irrational numbers, again, are numbers like the square root of 7. Can't be written as a fraction. When we put it all together, like I said, this makes the bucket of real numbers. And so Q is a subset of R. Q is a subset of R. Another thing to note is that rational numbers and irrational numbers, there's no numbers that overlap. There are no irrational numbers that are also rational numbers. So we say that those two sets are disjoint. Right? We say that those two sets are disjoint because they contain nothing alike. Your turn. I'm going to give you the numbers, and your job is to determine which sets they belong to. Notice I use the plural, sets. right? So what we're going to do is we're going to use W, Z, Q, and R for each of these. Again, whole, integer, rational, and real. R stands for real numbers. So I'll do the first couple with you. It may be helpful as we go through these to refer back to this diagram. In fact, I think what I'll do is I will copy that picture. I'm going to paste it so we can look at that while we do this. So the first one we'll talk about is number 1, which is -12. Where does -12 exist? If you start from the inside out and ask, is it a whole number? The answer is no, because it's negative. It is an integer. It's a z. So 1 is a z. -12 is an integer. And if it's an integer, it's also inside the rational numbers. So it belongs in Q, and it's also inside the real numbers, R. For number 2, we're at the square root of 15. Now, if you try that on your calculator, you'll see that's not a whole number. So that means it is an irrational number. It can't be written as a fraction. So the square root of 15 is an irrational number. And we are then just classifying it, for this case, as a real number. It's not over here. It does not belong over here. So it's only a real number. Okay. Number 3, 0.23. Is it a whole? No. Is it an integer? No. Is it a rational number? Maybe. It's a decimal that terminates, which means, yes, it can be written as a fraction, 23 hundredths. So that means it is a rational number and then also a real number. So take a moment, pause the video, and do the rest of those on your own. All right, number 4, 130. That is a whole number, which means it's also an integer, which means it's also a rational number, which means it's also a real. 3/5 is not whole or an integer, so it's a rational number and also a real. Number 6, 0.27, it's got the bar on top, which means it's repeating. That means it is a rational number. Repeating decimals can be written as fractions, so it's a rational and also a real. The square root of 10, that's an irrational number, so we're only classifying it here as a real. And the square root of 25 has a whole number root, 5, which means it's a whole number, an integer, a rational number, and a real number. Did you notice that every single one of these was a real number? There is something called a complex number. You might learn that in another math class someday. So one of the things you'll need to be able to do is classify numbers by these groups and by these sets. Knowing this chart here and knowing how to write that Venn diagram will be helpful, very helpful to you as you work through that. So the next part of this video talks about the properties of real numbers. And we've seen properties of all these different types of sets of numbers so far throughout this semester. Whole, integer, rational, real. They've got this increasing sequence, right, with each number contained in the next. And although they have several properties in common, like commutative, associative, distributive, each number system really was developed because it had some properties that other ones didn't. For example, whole numbers don't have inverses, right? So if you think about what an inverse is, 5 and -5 are additive inverses. Well, 5 is a whole number, but -5 is not. -5 is an integer. So we needed to create the integers in order for there to exist an additive inverse. So what we'll do here now is kind of put it all together. There is one new property, right? The real numbers, they have all of the properties that we've talked about within this course so far. They have closure under addition, closure under multiplication. We've got commutative property of addition and multiplication, associative properties of addition and multiplication, the identity properties for addition and multiplication, inverses for addition, inverses or reciprocals for multiplication, distribution of multiplication over addition. We've seen all of those in these subsets, right? These subsets, we've added more and more properties. So the real has all of them and one additional new property called completeness. So real numbers has all the other properties plus completeness. And so intuitively, when we just think about it, this really means that every single line segment, if you think about a number line, we'll just start at 0 and go up. Every single line segment can be measured. If I say, what's the distance of a line from 0 to, say, this point right there, I can measure it and state its distance with a real number. That was not true when we were just working with rational numbers. We learned about that in the previous video. Remember our triangle that was 1, 1, radical 2, and we said that square root of 2 was measurable, but we couldn't represent it with an actual written stated number. So completeness can also be stated using some terminology from earlier in the course. Completeness of real numbers means there's a one-to-one correspondence between the real numbers and points on a line. One-to-one oops, I put that right in the middle of the picture. One-to-one correspondence means every element in one set can be matched with a single element in another set. There's an equal number of them. So if you think about points on a line, there's a point, there's a point, there's a point. Imagine all the points packed together so closely on a line that there's no space that exists between them all. Every single point can be matched with a real number as well. Something between above and below 0, right? And so that's the idea of completeness. And no other number set has that. No other number set has that.